Now, let's talk about the Kepler's law. These laws can give you most of the parameters for the planet motion in the solar system. Okay, it's proposed by Kepler a long time ago, before the Newton's age. So the first law is called the law of the orbits. It says that all the planets moves in elliptical orbits with sun at one focus. You know that for any elliptical orbits, you have two focus. One is focused here, another focus point is here. The sun is always located at one of the focus. The second law says that a line that connects a planet to the sun sweeps out equal areas in equal time interval. So from here to here and from here to here, if they traveling for the equal time interval, okay, and that's because at this side it's moving faster. And this area sweeping by the straight line connects the planets and the sun. So this area should be the same as this area. This law is to determine the velocity of the planet at different position. Okay. And the law of the periods. The square of the period of any planet is proportional to the cube of the same major axis of the orbit. So the same major axis is kind of like the radius of the circular motion. So it measures the size of the orbit. So the size of the orbit, okay, or approximately the radius of the orbit, okay, is actually related to the period. So, in other words, it means that for those planets, if it's very close to the sun, the period should be small. If it's very far away from the sun, the period should be large. So 1 year in the Mercury is smaller than 1 year in on the Earth. And it's much smaller than 1 year in the, like say, Neptune or universe. Okay. And these laws proposed before the discovery of the Newton's laws for the motion and for the gravitational force. So there is no theoretical calculation available at that time. And Kepler find these laws by purely feed the astronomical experimental data. Okay, because we can observe the position of those planets in the sky at different time. Okay, he has those astronomical data, and he do the purely mathematical feed and find these things. So it's very amazing. One can do that, okay, without any guidance. You just try all kinds of possibility and see which one can give you all these that fixed. Okay. And it's especially amazing that he proposed the elliptical orbit. That's quite counterintuitive, because at that time people all believe that the orbits of all the planets will be perfect circular motion. Okay, but he proposed the elliptical orbits. So that's a Kepler's law. And one thing I would like to note is that after the Newton, all the three laws can be proved, okay, from the Newton's theory. We can try this one. The law of the periods. The square of the period of any planet is proportional to the cube of same major axis of its orbit. To kind of prove it, we can think about a simplified version, circular motion. Okay, it works because these this shape is exaggerated. In fact, those elliptical orbits are quite close to the circular shape, so almost the same. And so we can think about for the circular motion, you remember what we have done for the geostationary satellite. We see that you calculate the speed, to calculate the period of the satellite. In this case, it's a planet. T equals to 2 pi v over r. On the other hand, the v and r is related by this one. Okay, from the gravitational force provides a centripetal acceleration, you can get some relationship between the velocity and the radius. From this one, okay, this is the mass of the, in this case, is capital M is the mass of the sun, small m is the mass of the planet, and the mass of the planet doesn't matter. It will be cancelled. So you get Gm, and one of the r is cancelled here. You get Gm over r equals to v squared. Okay? And then it means v squared, okay, v squared equals to Gm over r. And then let's look at this equation. If we want to get rid of v squared of v in this equation, because we want to find some relationship between t and r, so we want to get rid of the velocity v, we can square this and both sides. So for this one, you get t squared equals to 4 pi squared v squared over r squared. Okay. Or t squared over t squared r over 4 pi r squared, okay, squared equals to v squared. Okay. So this one equals to v squared, this one equals to v squared. So Gm over r should be the same as t squared r squared over 4 pi squared. Okay? And then you rearrange this equation, you get t squared equals to G, okay, 4 pi squared Gm over r cubed. Okay, I think I did something wrong here. Why is it inversely proportional to that? Okay, let's check. Oh, sorry. Okay, it's 2 pi r over v. So here, it's t squared equals to 4 pi squared r over v squared. Okay, so v squared equals to t squared over 4 pi squared r squared. Okay. And let's see. Equation t squared over 4 pi squared r squared over v squared. So v squared equals to 4 pi squared r squared over t squared. Okay. So you get this one equals to v squared. This one equals to v squared. So you get 4 pi squared r squared over t squared. And you rearrange this equation. You get t squared equals to 4 pi squared over Gm, okay, multiplied by r cubed. And this is a combination of all the constants. Okay, so you can see the square of the period is proportional to the cube of the radius. Okay, it's kind of proof. The third law of the third Keplers law. Okay. And also you can actually prove the first law and the second law, but we are not going to do it here. And I also would like to talk about the Lagrange points. Okay.